Welcome everybody on this webinar on hybrid generator systems. My name is Johannes Boonstra, and today I would like to tell you something more about the generator systems, how they're being used, and also what the benefit is, and how you can also for yourself decide if it's something for you or not, of course. I will not do this today alone because there are a lot of people who are sent an application to join this webinar. So I was afraid that I would have too many questions for me to answer and that it would be dragging on too long. So therefore I asked a few colleagues of mine, Andrew Perry, he's an expert of hybrid generator systems. I've been working for them for many years. Also Bob Hopman. Bob Hopman is a very technical sales colleague of mine, also involved of doing a lot of trainings by himself in the German area. And Henrik Nielsen, he is a technical sales manager in Scandinavia, also doing trainings there. If you have any questions, please use the Q&A bar on top of your Zoom. That makes it easier for us to answer your questions. Andrew, Bob, and Henrik will take care of them. And if not, if we're overflooded with questions, we will do that later because there will be room enough later on to answer these. So yeah, let's get going. The webinar is about how to make a generator run more efficient. Generator is something which have been used for many years, but with an add-on with our blue boxes, you can make these kind of systems much smarter. And much smarter, I will explain to you later, but has a lot of benefits. Traditional generators, so a diesel engine connected to a generator to produce electricity, has been used for many years and also has a lot of applications. You will see these generators in the utilities, oil and gas industry, mining, constructions, events for temporary use, and also many other applications. How many generators there are, I don't know, but they are still being used quite a lot, and also this number will increase the coming years. We can see that on the rental market because a lot of projects run on electrification and need more and more electricity to run. Therefore, the rental generator market is also increasing. At the moment, that's an estimate, it's about $10 billion US, but for the coming years, that could well be over $15 billion US. That means that that market is substantially growing. And that's because more and more projects need electricity to run. A traditional generator, if you look at the cost of them, basically you can split it up in three things. First of all, of course, the investment of the system, but more important is the running cost of the generator, which are the fuel cost and also the maintenance cost. Well, you know, of course, what's happening in the world, especially the fuel cost is rising and more basically every year. So if you could optimize the fuel cost of the generator, the whole project would be more optimal. The fuel cost is not only the liter cost of the gallon cost of the diesel, but it's also the transportation. You can see on the picture here a few applications. You can do that with a truck, to drive to your generator and then refill it. But some locations have even more difficulties refueling. You can see a picture with a helicopter. And then the fuel price can be, well, a few dollars only for the liter, but to get that fuel into the tank of the generator can go up to $200, $300, $400 per liter. That means saving diesel on these kind of systems not only affects the cost of the diesel by liters, but also the total cost of getting that diesel to that location. So it's more than only the cost of what a liter is costing. If you look at the fuel consumption of a generator, you can split it up in two. You have the idle power consumption and you have the power consumption when generating power. And these two, together with these two, basically the total fuel consumption is realized. If you have a generator running with no load, so an idle running, it still produces, it still uses a lot of energy to get that thing running. Because to get a certain voltage level and to get to a certain frequency, the generator needs to run at a certain speed. And to run at a certain speed means that you also have to burn diesel to get that going. So without any load on the generator, you're still burning fuel, so to say. For a medium-sized generator, it can already be several liters per hour. So if you have an application where the load is near to nothing, so the generator is actually only idling, then still you're going to use a lot of fuel over a 24-hour period or over a week period or even over a month period. So that's something to consider. If you look at the average fuel consumption on a traditional generator, you can see a small graph here. Well, if you have a small 10 kVA generator, it can be, well, 0.8 or 1 liter an hour. But if you go to the more powerful generators, 50 kVA, 75 kVA, 100 kVA, they even burn 7 liters an hour. If you would, for example, have a 50 kVA generator running for 24 hours, it would already cost 84 liters to do that. So without generating any power, that would be the fuel consumption of the generator running basically to maintain a certain voltage or to maintain a certain frequency. Besides the idling power, there's also, of course, the power generation consumption. That means the more energy you generate, the more fuel that generator will take and able to do that. The point is actually that the generator size is typically chosen for the worst case scenario. That means if you have an application with several loads, that generator must be able to supply the power to all that loads. If it is able to supply that load, there will be a time during the day or during the week that system will just stop running because, well, it doesn't work. The thing is that because of the generator is chosen for the worst case scenario, that typically the load of the generator is far less on average than what the generator is capable of doing. Looking at the generator on a typical time scale, then you would see that only, well, 5 to 15% of the time the generator is actually working what it's designed to do. And the rest of the time it's just working far less. That means that the overall efficiency is far from perfect because the generator is running the best at a certain high load, because otherwise the idle consumption takes a big part on the total fuel consumption of that generator. If you would look at the system, and this is just an example, so don't pin me down to the exact numbers. But if you look at the system, basically the generator is being chosen for the largest load of combination of loads, of course, that will be occurring during the day. And during that period, the generator will do this on an optimal way of generating power. Most of the rest of the day, sometimes there is a peak. A peak power can occur if you have to start up an electrical engine or something. But most of the times, the power is far less than that largest load of the combination of large loads. So the average load in a system, and that's also what you see typically on the generator system, is about 5 to 15%. That means the generator is just waiting until there is a large load or something has to be started up, and then actually the whole power of the generator is used. A lot of time around this, the generator is just, well, almost idling or doing a few percent of load. That's basically also the problem of inefficiency of a generator system. If you look at the overall efficiency of a generator, you can say, well, how much energy would theoretically be possible to get from a liter of diesel? Well, a liter of diesel contains about 10 kilowatt of energy. If you look at how much energy you could theoretically get from it, it's 10 kilowatt hours. But the generator, of course, has also inefficiency built in. That means you lose power in the diesel engine, but also in the electrical part of the engine. Typically, you can see at the graph here on the screen that if the generator is running about, well, 80, 90%, then the efficiency is about 30%. So that means each liter of diesel can more or less generate 3 or maybe a little bit more than 3 kilowatt hours. If the generator is running on a less high load, then the efficiency drops down. So if a generator is idling, of course, the efficiency is 0. But if you would run at, well, let's say 10%, then the efficiency would be, well, about 10%. That means that same liter of diesel with an underloaded generator would only create about 1 kilowatt hour of energy. So the more you are able to load the generator optimally, the better you get the power from a liter of diesel. So it makes sense to look at how to load a generator in a system to be optimal on your generator fuel consumption. If you look at that in an overview, you can see here for different kind of generators, what the typical load consumption is, what the typical fuel consumption is. And you will see then that if the load goes up, also the fuel consumption goes up, of course, but it doesn't go up that fast as the extra power that you generate. If you look, for example, for a 50 kVA generator on a 24-hour period, then you will see that on a 10% load, which is, well, about 5 kVA, so let's say 4 kilowatt, it takes 120 liters. If you would do the same with a 90% load, it would, of course, take a lot more diesel to supply that 90%, but at 90%, you would supply also a lot more energy. You can see on this slide what then the cost per liter is. Because if on 10% load, you take 120 liters and you're creating, well, 10%, that's 5 kilowatts times 24 hours. You take 120 kilowatt hours and you divide that by the number of liters that you took. That means that the result is that the generator is taking 1 liter per kilowatt hour. If you would load the generator at 90%, it would take 288 liters for 24 hours. But in the same time, that generator would generate 1080 kilowatt hour. That means if you're going to divide that, the 1080 by 288 liters, then for the same generator, it would then produce 3.75 kilowatt hours per liter. That means you get almost 4 times as much energy from the same liter than you would have if your generator would be running at 10%. So having the generator running at 90% would save a lot of fuel by generating the same amount of energy. If the generator is underloaded, it's not only a problem for the generator in terms of fuel consumption or efficiency, just how you call it, but also mechanically. An underloaded generator is also under temperature. That means the temperature of the generator will be less than where it's designed for, and that creates also issues. If you have a low temperature in your generator, just like a cold engine of your car, the exhaust will also be more. That means also pollution-wise, fume-wise, you have a worse scenario than if the generator has the optimal temperature. So the combustion is better at the higher temperature of your generator. The colder the generator gets, the worse also your combustion will be. If you have an underloading for a lot of time, for the majority of the time, then what you also will see in your generator is that you will have glazing. And glazing means, well, on the surfaces of your cylinder walls, there is unburned oil, and that unburned oil that creates a sort of a layer, and that layer prevents the lubrication of your generator. So basically also lifespan-wise, glazing will affect negatively the lifespan of your generator. So an underload generator has less lifespan than a generator which is optimally loaded. The same goes, of course, for pollution due to the fuel, which is partly burnt because of the temperature of the exhaust zone is not high enough. Also, you will have more pollution in your system. So, what is then the trick to have your generator system, a traditional generator, run more efficient? We have a brochure. Later on, there is a link for that brochure also. And then we claim, well, if you have a hybrid generator system compared to a traditional generator, you can typically save up to 80% on fuel. Well, the trick is to have the generator running as little as possible, but if you have it running, run it as optimal as possible. So avoid the idling or the almost idling of a generator and make sure that you only run the generator at the optimal level. That leaves you, of course, with the problem that the rest of the time when the generator is not running, you also don't have voltage and you don't have a frequency. So a hybrid generator system has in line with itself, so between the generator and the loads, an inverter system. And that inverter system will supply 24/7 a voltage and a frequency. And only when needed, then you will switch on the generator and the generator will help then that inverter. In the picture below, you can see here that on the gray area, and that's typically in the morning, the generator is started, it fuels up your battery system, it charges your batteries, and then the generator is just switched off. Only when you have a large load for a longer period of time, then you can switch the generator on, but besides that, the generator stays off as much as possible, and the inverter system, together with the batteries, will supply the load. Well, this is also what it says. If you have a generator in a hybrid system, you only start it when there is a peak power demand or when the batteries need to be recharged. Well, that's something also what your inverter is able to do, because your inverter is able to look at the battery and is also able to look at the load, and therefore can also decide when the generator should be running. If you have a system like that, then the generator is running as little as possible, and when it's running optimal as possible. If you have the inverters in that system, they follow the demand of the loads. And the nice thing of that is that an inverter doesn't need to be so careful in which type of load you are, depending on a generator. A generator has a bad efficiency at a low load, but an inverter already has a high efficiency at a low load. And it doesn't really matter on which spectrum of the generator power, sorry, the inverter power that you are, that efficiency is always pretty high. Especially on the lower load side, the inverter performs very well. So if you have a system and the load on that system is typically kind of low, then the inverter efficiency is improved. That means the whole system will benefit from the fact that you have an inverter on its output. If you have a hybrid generator system, the roles are swapped. So normally spoken, the generator is in charge and it is the primary source of power. But with the hybrid generator system, the inverter becomes the primary source of power, and the generator acts as a sort of a battery charger and also an emergency when the power is too long for a certain time. Well, if you have an inverter in line with your generator, you also have an increased peak power capability. In the inverters, maybe you already know that, we have a system which is called power assist, and power assist means on top of the energy what comes in, you can bring your inverter power. So when you have a high peak power demand, the inverters will help the generator also to supply that peak power. And therefore also, you're able to be more flexible in what kind of loads you connect to your hybrid system. Well, this is a small example. What you will see here is how you can save 80% of fuel. If you have a traditional 550 kVA generator and you would run that generator for 24 hours at a very low load, so let's say less than 10%, then the fuel consumption of the generator is something between the idle load and 5 liters per hour. That means if you would do that, if you have the generator running for, well, let's say 5, 6, 7%, then the total fuel consumption is about 120 liters. If you would add a hybrid system to that generator, then basically the generator only would be running to supply that energy. And that energy, what the whole 24 hours would be needing, could be generated by that generator in about 2 hours. So 2 hours running equals the same of energy than an underloaded generator for 24 hours. That means if the generator is running for 2 hours, but on a high load for 90%, it would take about 12 liters per hour, which is 24 liters. And that means for that whole day of supplying that low power, on the traditional setup, you would use 120 liters, but on a hybrid generator system, where the generator is switched off, you would only need 24 liters. That means you will be saving 96 liters, and that's about 80%. That means if you have an underloaded generator, adding a hybrid system to that will make an enormous fuel saving. But of course, it's not only on fuel, it's also on the mechanical part of the generator, and that's the maintenance. The maintenance is basically something which is also included in the running cost of a generator. Well, if you look at the typical generator, let's say 25 to 75 kilowatts, the service interval is between 500 and 1,000 hours, or once a year, just what happens first. And the cost for a service job is about $1,000 each time you have to service that generator. The lifespan of a generator, more or less, is about 10,000 hours. Well, if you have a traditional setup generator, so a generator which runs all the time, that means it should run 24/7, and that means every 6 weeks, you would have a service job done. If you look at $1,000 per service job, that would be $8,500 per year. If that same application would have a hybrid generator set up, you only have to run it for 2 hours per day, so 2 times 7. That means instead of having each 6 weeks a service job, now it only takes each 70 weeks a service job. Well, then the first year, 1 year comes first. That means then a traditional setup takes about 8.5 times more maintenance cost than a hybrid generator setup because of the limited hours of running that the generator is doing. A hybrid generator system isn't only better on the business side, so what you do with your calculator on maintenance and on fuel, but it's of course also on all other imaginable parameters. For instance, emission. You have far less emissions if your generator runs far less. You also have far less noise because, well, the generator is switched off. Also the overall logistics to get the fuel to the site where the generator is at. And also, of course, you have an uninterrupted clean power supply all the time. That means if you have to switch from one to the other power source, the inverters take care that it goes completely seamlessly and you don't have to worry about dips and spikes into your system. Well, how exactly can it be done? Well, of course, between the generator and the loads, you have to build a system. Well, that system consists about inverter charges, and these inverter charges are bidirectional. That means they can charge and they can also discharge from the battery and produce AC. The nice thing about having a multi or a quattro in your system is that the multi knows exactly what the load is doing. It sees the current, what is coming from the generator to the load, but it can also, of course, look at the current which goes to the battery, and it has the ability to know what the state of charge of the battery is. So it can decide on these two parameters when the generator should be started. If the battery becomes lower than a certain level, what you have preset for yourself, or the loads comes higher than a certain level, then you can decide, okay, now it's time to run the generator. And in both cases, so on load, but also on low state of charge, well, then the generator is being loaded optimally. What is important in a hybrid generator system is the balance. It's the balance between the generator and the inverter charger and the battery, of course, but also the load. So if you want to decide to design a hybrid generator system, you have to know, well, what balance causes what. First of all, and that's a very important one, is the generator power needs to be at least equal to the inverter power. It's very tempting to say, okay, let's take a very small generator and a very powerful inverter, because then, well, I have less investment on my generator and the inverter will take care of the load. Well, the risk of an out of balance load between a generator and an inverter power is that the voltage regulation will not work very well. In a system when a generator is running, the inverter and the inverter charger will be paralleled and synchronized to the generator. And if the inverter power is too high, so let's say you have 10 kilowatts of inverters, but your generator is only 5 kilowatts, then the voltage regulation of that generator will be affected by these inverters. That means you cannot load the generator optimally anymore because the voltage will jump up and down. Well, the rule of thumb for that is that the generator power should be at least matching the inverter power. So a 50 kVA generator also needs a 50 kVA inverter power, or less, of course. You can run a bigger generator on a smaller inverter, but not the other way around. The second thing is the inverter needs to power the load at least for a few minutes, because if the generator needs to be started, it takes some time before the generator actually supplies power. The generator is started and then the inverter needs to synchronize with the generator, and then you will be passing through the energy from the generator to the load. That whole process takes some time. So let's say that takes a minute. In that minute, the inverter must be able to supply the load. If the load is so much bigger than what the inverter is capable of doing, the system will switch off. So yeah, the load will also be not powered anymore. So in worst case scenario, the inverter needs to be able to supply that load for a few minutes. The third thing is the pass-through power. So the generator has a certain power, and that has to be transferred to the load. But together, to supply that load, also energy must be supplied to the battery. And the total of these two, so the battery charging power and the power to the load, is coming into the charger inverter, so the quattro or the multi. That means the pass-through power of this inverter system must be able to handle the total charge power plus the load at that time. And the battery, of course, that's the last one. The battery needs to be able to supply all that load for a few minutes. If your inverter system is big enough, that's nice, but the inverter doesn't create energy. The energy is being drawn from the battery. So the battery needs to be powerful enough, so the discharge current needs to be high enough to supply the inverter with a lot of energy so that it can do its job. And if it's, well, on high power load, then it must be long enough to be able to start the generator. Well, with our products, we can parallel and we can make a larger system from different units. So if you have a multi-compact or you have a multi-plus or a quattro, they can all be switched in parallel. The largest unit that we have is 15 kilowatts. And remember that it's better to have one large unit than several smaller units in parallel. That means 3 times a 5K, which is also 15 kilowatts, is not as optimal as one 15K. One 15K unit will simply do more than 3 units of 5K. And basically, the reason for that is that you have to symmetrically make sure that all the current go to the various inverters. So your wiring and setting up must be exactly the same in order to get the maximum power. If you have one large unit, you don't have to worry about that. If you want to parallel units single phase, you can do that up to 6 units for 10 kVA units, or less of course, which is maximally 60 kVA. You can also do it to 15 kVA units, and then you can up to 5 units being paralleled, which is 75 kVA. This is single phase. If you're going to parallel, then all units need to be identical. So you cannot parallel a 5 kilowatt with a 15 kilowatt. You can only use the same units, and also in age, by the way, to have them paralleled and becoming one large system. You can see that on the sticker on the unit. The units have a certain serial number, and on the serial number you can see the date, what kind of production date it has, and also on the software you can see which kind of unit it is. That is not only on power, but also on the transfer capability and also on which processor is being used. And basically the whole first digits of your software version should be identical. If that's identical, that means the model is the same, the processor is the same, and you can easily parallel these units and also put them in 3-phase if you want. A 3-phase system, which is actually quite common in hybrid generator system, is a system that the units are being connected each per phase. So you have 3 legs in a 3-phase system. Each leg gets its own unit, and these units are being 120 degrees shifted from each other. That means they still produce 230 volts if you have 230 volt unit, but between the legs, so between the first unit and the second unit, you have a higher voltage because the voltage is out of sync. That means you have 230 and also 400 volt in this case. That 400 volt means that you also have less current. That means it's easier to install, so you can have less thick cabling, and also the start-up powers of high loads is being limited because of that higher voltage. Also, of course, because it's already a rotation in a 3-phase system, it becomes much easier to start up engines and so on. The last benefit also on a 3-phase system is the ripple effect. The ripple, which is, well, basically the AC component on your DC, so on your batteries, is being less because also the ripple will be phase shifted, which means that the nominal ripple will be less. So for the battery system, and also for the issues you can have on that side, also 3-phase is more optimal. So a lot of hybrid generator systems are all built in 3-phase. If then 3 units, each unit per leg is not enough, you can also extend the power of each leg, and you can parallel units per leg. That means, like you see in this picture, you can have 2 or 3 or 4 units parallel per leg, which increases the power on that, and then the whole system becomes much larger. If you would do that with a 15 kVA system, if you have 5 systems per leg for a 3-phase system, you will be looking at 225 kVA, which also means, of course, that the whole rest of the system should match that. So also your battery must be able to supply that load to that inverter system and the bus bars and so on. If you have a 3-phase system, there are a few things to consider. The first thing is that each unit is independent in a 3-phase system. That means unless a generator, one leg has no relationship to another leg. So the nice thing from that is just remaining the 230 volt inverter that it is, and it can be also used or not. So if you have a full load on leg 1 and nothing on phase 2 and nothing on phase 3, then with a traditional generator that would be an issue because the rotation would not be as smooth. But for an inverter that doesn't matter. There is no negative side on having the loads differently spread on the legs. So that's a big benefit also if you have a load in your system which is not balanced that nice. Equal loading is only important for generators, not for inverters. If you have a 3-phase system and the generator is running, these inverters will not balance out the generator. Some people have the idea that it will happen that way, but that's not true. If you have a 3-phase system, they work independent of each other. So if the load is also unbalanced, that means also when you start the generator will still be loaded unbalanced. The charger makes it a little bit better, but it's not that one phase will supply energy to the other phase to make all work nicer and easier. Also, one thing to consider is, of course, the 3-phase rotation. You have a certain sequence, L1, L2, and L3, and that inverter decides which one is L1 and which one is L2 and which one is L3, depending on how you programmed it. So the sequence of programming is also determining the rotation of your 3-phase system. That has to match with the rotation of the generator, because if the generator has a different rotation than how you programmed your inverters, these inverters will not be able to accept the power from the generator. You will get a warning then on your screen of your color control or of your servo that there is an incoming power, but the phase rotation is wrong. Well, you can do 2 things then. You can, of course, reprogram your 3-phase systems and have another unit swapped on L1 and L2, but you can also do it wiring-wise, of course. You can also install the wiring to your system differently. Yeah. If you have a mobile system which is used on different locations, you could also use an extension cable where the phase is already crossed, or you use a switch. So you can switch the rotation of your system so that you're always able to be connecting to that generator which you have on that side. Some special application, and I just want to mention that here. If you have a 3-phase system running, you don't necessarily need a 3-phase system to feed it. You can have a setup of your 3-phase system so that it also allows you to feed it with a single phase. That single phase, in this case, will go to one unit. That has to be L1, and L1 is then the master of the system. So L1 is passing through that energy, what it gets from the single phase, and pass that on to the load. And that makes sure that the other phases, so L2 and L3, will stay exactly at 120 degrees different from L1. So the 3 units together will create 3-phase, but only L1 will pass through the power which it gets and also will supply DC power to the battery. So if you have this running, L1 will charge and will pass through, and L2 and L3 will only make 230 volts from the inverter, but at a set voltage shift from the other, so that you always have a guaranteed 3-phase network. You make this setting in a VBus system configurator by deselecting switches group. If you do that, then the units can switch independent of each other. Beware, if you have a single phase which you want to connect to this system, you always have to use L1. Together with L1, you can also use L2, and if you have a 3rd phase, you can also use L3, but it's important that at least L1 gets power. If you're paralleling a system, you have to have these units communicate with each other. That means you have to interconnect them, and that interconnecting with our product is done by an RJ45 cable. The protocol that we use is VE-bus, which is our own protocol, and that makes it not important how you wire, which sequence you wire the inverters with each other. As long as they're all daisy chains, or all get in contact with each other, then later on you can program them in a certain role. You have to make sure, though, that they are properly connected. Always use cables which are having a high quality. We see a lot of people making their own cables. Sometimes that works fine, but a lot of time that doesn't work fine. And then, well, you have issues that people get unexpected errors and so on. So make sure that you use the correct cables. Doesn't necessarily need to be a Victron cable, but at least a good quality UTP cable. If you have done that, you have the options of taking a software program. Well, in this example, a VE-bus Quick Configure. VE-bus Quick Configure is a small program which you run on your laptop. And on that, you can program up to 3 units. These 3 units can be set up in different setups. You can have them parallel, you can have them in 3-phase, you can have them in split phase. And basically it works like a small wizard. It's going to ask you a question what you want. You press next, and then you get a new question and you press next again. So in no time, basically, you have programmed your system in 3-phase or in parallel or whatever. This is limited to 3 units, so it's actually for the smaller systems. There's also a program for the larger systems, which is the VE-bus system configurator. And with that, you can have more units programmed, and you have also more options how to behave on a load or on charging side. Here you can also do the switch as group, so that you have a single phase in and a 3-phase out, if you want to do that. You can connect the units to your laptop using a converter. And the Victron, that converter is called MK3. And MK3 has a USB side to plug into your laptop, and the other side is a VE-bus. So that's one is being used to connect to your system with. On the bus bars, which is also important, of course, because you have to distribute all your DC power to your system, often the links distributor is used. The links distributor line is a fancy bus bar, and that bus bar enables you to fuse all the incoming and outgoing groups. We have also a links smart BMS, which is being directly used for smart lithium batteries, and that smart links BMS also has a contactor in, so it can also work as a main switch. A bus bar, what we have is up to 1000 amps, and for the moment the Link Smart BMS is 500 amps. That means about 30 kVA. There will be a larger model in the future, but up to now 500 on our lithium systems is the max. Of course, you can also use the links distributor with the VE-bus BMS, and the VE-bus BMS is independent, connected to your batteries and to your the rest of your system, to your servo and to your inverters. And then you can use basically any bus bar that you have made for yourself or that you have bought for yourself. If you're going to connect the units to the bus bar, you have to make sure that you do it as symmetrical as possible. On a 3-phase system, that's not that important because, well, one phase is completely isolated from another phase. But if you have a parallel system or you have 2 units per leg, so to say, then it's extremely important to have the cabling and also the length of the cable exactly symmetrical. Only then you have the optimal and maximum power from your system available. Also, you have to fuse, of course. If you fuse units, you fuse the units per unit. That means you don't add up the cables from 2 or 3 units to one large fuse, because if something goes up and something goes wrong, then that fuse has to trip at a much higher level. So if you have 2 units, or you have 3 units, or 4 or 6 or whatever, then each unit gets its own fuse. Make sure that that fuse is also the same size and for each unit, and that's also to ensure that the balance between the unit is as optimal as possible. If you have bus bars in your system, it's also important that you feed them well from your battery. Well, below here you can see a few examples. Well, the first one on the left is wrong because the thickness of the cable from the battery to the bus bar is the same as the thickness from the bus bar to the inverters. That means that the cable from the battery to the bus bar, in this case, will be highly overloaded by the inverters. What also is wrong is the one in the middle, which has the plus and the minus on the right of the bus bar. That means basically that the voltage distribution of this system is not equal. The unit on the right will have the highest voltage, the units on the left will have the lowest voltage. Well, especially when you have a single phase parallel system, this kind of bus bar connection is creating an unbalance between the units, and therefore you will never have the optimal power from your parallel system. On the right, you can see how it's done. You have the plus on one end and the minus on the other end, and also the cable thickness is up to the job. That means the cable thickness is far thicker than from the battery to the units. That was on DC, but also on AC. And AC, a lot of people don't underestimate that, but also on AC, it's very important that you have the correct balance there. That's because the power which is drawn from the DC to the unit will also end up on the AC side. So if you have a different resistance there from one unit to the other unit, also you will create an unbalance. This is because internally there is, of course, a small difference between the units. And if your wiring is not done correctly, then also this will result in an unbalance. I have a small drawing over here. What important is, if you have a parallel system, is that you don't overdo it, because if the cable resistance is much lower than the internal resistance of the unit itself, it means that the influence of that internal resistance becomes leading in the balance. Normally spoken, we say, well, keep the battery cables as thick, as short as possible, because, well, then you have less losses and also you have less ripple in your system. But if you overdo it at paralleling, a single phase paralleling, that means that that thick and short cable will actually create problems. So you have to find a balance in doing it correctly, as thick, as short as possible, and while making a little bit more resistant in that system. So if you normally handle the specifics of the cable, then you would do it right. If you have the cable too thick and too short, you have to be very careful, because then only the torque of a bolt somewhere can already cause the difference between having a nice balance or having a very bad balance. So when you have a hybrid generator system, how can you calculate then on which components you have to use? Well, basically, you have two things what you have to consider. First, of course, is your inverter charger system. The second thing is your battery bank, and these things have to work along with your generator. The important question to ask is what inverter charger is needed, what battery capacity is needed, what is the charge current which is needed, that's the power coming from your generator, of course, also, and also, is there a quiet time required for the generator? Because if you have to the ability to switch the generator off, you can also have the desire to say, well, I don't want my generator in specific time frame, because, well, the generator is placed in the neighborhood, or you have other reasons for that. But you can, of course, decide when to switch the generator on and off. This means that you have to take into account, well, if the generator is off for this specific period, then also my battery has to be able to compensate for that. Well, I made a small drawing with 4 questions, and basically these are the steps how to go into a calculation of a system. Well, if you look at step 1, and which is the most important one, that's the step which determines the load of your system. That means the system needs to be able to supply this load, and the calculation that you do depending on that. So you have to list how big your loads are and also at which times they are used. So you can predict also the system that you need for it. Step 2, that's of course the inverter calculation. The inverter calculation depends on step 1, which powers that you have to load, but also the peak requirements. The inverter is very good in handling peak loads, but you need to know what kind of peak loads you can expect. The third is, of course, the power in calculation. So that's the power which comes from a generator, And that's depending on how you're going to recharge your batteries again. Normally, you have a generator for the high power recharging, but you can also think of PV systems, so that you have a PV system charging your batteries during the day, or if you have a wind turbine, and also that wind turbine will supply you with energy. Well, together, all these power in calculations, together, they decide how to charge the battery, and also how often it's needed to run the generator. Well, then the step 4, that's on the battery calculation. And the battery, of course, that's one of the most important calculations in the system, is the autonomy. So how much time can the system run on the battery, but also the depth of discharge. So how far do you want to deplete your battery before the generator has to be restarted again? That is, of course, leading for which kind of capacity you have to install in your system. And together with these two, you have the charge rate. So how fast can you refill that battery? And also the discharge rate. So if you have a big load, is the battery able to generate the power to supply that to the inverters? Well, what is important in making calculations is that you always work on the same sizes, the same protocol, so to say. So always calculate in energy. And calculating in energy means that you don't use amps or volts or kilowatts or kiloamps or these kind of things, because that will most likely make the calculation able to do more volts. So always use energy. Energy is expressed in watts. Well, as you all know, of course, a watt is volt times amps. A kilowatt is 1000 watts. A kilowatt hour is 1000 watts during an hour. So if you have all the loads and all the power from your battery and also the power from a generator in watts, in energy, then most likely you make the best system without any mistakes. Well, the power calculations for your load, so to say, what it has to supply to the load, is basically a list of everything which is being able to connect it to that system. Most of the times, I can have you next slide. Most of the time, it's a typical type of things, and you have to look per item. Okay, I have to connect this. What power does it require? Does it require that power all the time, or does it require that only at night, or does it switch on and off? And then basically a list of these loads will come to a complete load balance. And then you know, well, this is the task that my hybrid generator system has to do to supply the energy for. Well, there are different types of looking into that. The top one here is the air conditioning. If you look at the type plate on a machine, that air conditioning says, well, my connection power is about 1200 watts. Let's say you would be running that for 10 hours. That doesn't necessarily mean that that airco is also using 1200 watts. That air conditioning is switching on and off its own compressor. That means basically the load factor of the that air conditioning is less than 1200. So if you would then calculate the energy from this airco for a complete 24-hour period, you could say, well, it's 1200 watts times the 10 hours, of course, and you have a factor of 0.5. That means, well, half of the time the compressor is actually running, and that means a total of 6000 watt hours per day. You could also say, well, I have a fridge, for instance, in this example, and that fridge uses 279 kilowatt hours on a complete year. Then you have to calculate, okay, if that's the yearly consumption of this load, what would it do per 24 hours? Well, simply dividing that by 365 days, and then you will have, in this case, 764 watt hours a day. You can also have a load like a pump. A pump, in this case, is 400 volts, so it's a 3-phase pump, and it uses about 1.3 per phase. If it's running for 2 hours, then you have two things to consider. First of all, of course, you can calculate the energy, what is needed to be running. In this case, it's, well, about 1800 watt hours a day, if you calculate that. But also, with this kind of load, you have to expect that there will be a high startup power. Well, a startup power on a 3-phase engine is about 3 times the nominal load. So in this case, when you have a 400 volt 1.3 amp unit, you have to expect that the startup power in this case is about, well, what is it, 4 or 5 amps per phase. So the inverter doesn't only have to supply the energy over time, but also has to be able to start up that pump to get it running. Well, if you have all these loads listed, you get the load balance, and that load balance gives you the amount of energy what you will have to do for the complete 24 hours a day. That means in this case, I just made some figures up. It's about 120 kilowatt hours per day. That sounds a lot, but if you divide it by 24 hours, it actually is not, well, it's not too bad. If you have to do that, of course, be realistic. Focus on the major loads in the system. If you have your laptop plugged in or not, that isn't really important when you calculate in hybrid system. So all the small loads, well, you can disregard them. Although, of course, when there are a lot of small loads, you have to add them up together. But be realistic on what you have and what you have to be powering. Yeah. And then, of course, if you have that load balance made, determine the peak power of the system. Because if you want to choose the correct inverter for a system, you have to see what is the peak power. Energy-wise, most of the time it will be fine, but the peak powers can make a system work or not. The peak powers, they are the loads that run the same time in the worst case scenario. So if you have an air conditioning running, then at the same time also a pump could start. So if you have these two added up together, that makes the power size of your inverter. So also be very careful at looking at peak powers of your system. Well, if you go back to the overview of the load profile of a system, you can see here that the peak power, looking at the inverter kind of thing, is basically kind of easy because the inverter is very good in handling peak powers. The largest load in the system, or the combination of loads, of course, that is determining the inverter size. So you add up what the nominal powers are, what could run at the same time. And then all in all, if you have the overview of all the loads, then you have the average load of your system. And that basically is determining how much energy has to come from your battery into your system. The inverter size, and that's really important, has to be more powerful than the biggest load of the combination of loads running at the same time. Because the inverter system is always number one in the hybrid system, because if that one will not be able to supply the load, then the whole system will be failing to supply that load. A good rule of thumb is to take the peak power of a system and take about 80% of that as a sort of worst case scenario with a safety margin, because you can overload an inverter a little bit. So that means if you have this rule of thumb, then basically you get the right inverter power. What always is important in an inverter system is that you have to realize that there is a duration of the power due to temperature. Every inverter, if it's becoming warmer, is able to produce less power. So how you're going to install your inverter means also that that has an effect on the maximum output power of that inverter. So if you have 3 or 4 or 5 inverters in a small cabinet, these units will heat up. It can also be the ambient temperature, of course, and that means effectively they can do less power than what is on the spec sheet. Well, you can see here a thing for a 3 kilowatt unit. Sorry, this is smaller even. It's a 1200 watt unit, and that 1200 watts will increase in power at the moment that the temperature will go up. That means realize that the higher the temperature is, the less power you can expect from your inverter. So make sure that ventilation and space around the inverter is done properly. So step 3, that's basically the generator, which is the easy one. You can know, of course, what the size of the generator is. And according to the size of the generator, you can also determine, okay, and this is the power, what can be passed through to your load. You have calculated your load already. And the extra energy, what is a generator able to supply, can be used to charge your batteries. So the top of that should be around, well, 80–90% of what the generator is able to supply. And of course, Besides having the generator running, you can also add some things like solar or wind. Everything what helps charging the battery makes that the generator is needed to run less. So the more capacity you generate besides the generator, especially when it's free of charge energy, makes the system more optimal. Well, and then this thing, the last calculation is the battery. The battery, you have to decide the system cycle period. The system cycle period is how often do you want to recharge that battery per day. You can do it 1 time a day, but that means you have to store the capacity in the battery for the whole cycle, for the whole day, so to say. You can also say, okay, I want to have the battery recharged 2 times a day, or 3 times a day, or 4 times a day. That has an effect on the size of the battery. On top of that, of course, the battery capacity itself. You have to calculate how much battery capacity do I need to install. And that's depending, of course, on the depth of discharge. If you discharge your battery to 50%, you have to almost install twice as much capacity than if you would decide to discharge the battery to 90%. So the depth of discharge is also a huge effect on what you will do with your system size and with your system investment. Of course, the other hand is the less you discharge your battery, also the higher your lifespan will be. Well, then the last two, it's the charge rate and the discharge rate. If you want to optimally have the generator run during charging, you have to have the power to charge the battery as close as possible to the optimal rate of your generator. That means if you have 30 or 40 kilowatts of room in your generator power, your battery and also your inverters must be able to convert that energy, which is coming from the generator, to be able to charge your batteries with that. So your battery needs to be able to accept that amount of energy during a charge period. If not, if your battery is limited in accepting charge power, that means that your generator will be running at the lower level, which also means it's becoming more inefficient again. So make sure that you have enough charge power and also the ability to charge that power actually in your batteries to have the generator run as optimal as possible. Well, and then of course also, and I mentioned that before, that's the discharge rate. And the discharge rate is that the battery must be able to supply the energy to the inverter in order to have the loads powered at all times. If you have a hybrid generator system, it cannot work without batteries, because battery is basically an extension of your inverters, and these two take care of the energy supply for the majority of the time. For that is also that the efficiency and the lifespan of the battery is a key factor for the return on investment. If you have to replace your batteries quite often, that means that the whole return on investment for a hybrid generator system becomes a very bad calculation. So make sure that your batteries also have a long lifespan and well, work optimally together with your inverters. For that, lithium is the most obvious battery to use in a system like this, especially when you want to recharge your batteries 2 or 3 times a day. That's basically unthinkable if you do that with lead. Lead also has a very bad efficiency while charging, especially in the top end. And that means, well, there's only one chemistry which is very optimal, and that's the lithium kind of batteries. So make sure that you pay attention on which battery you use, because that's also determining how efficient your hybrid generator will be at the time, but also over time. If you're going to choose a battery for your hybrid generator system, you have, of course, the option to go for a rather small battery setup, or you have the option to go for a well, rather high battery capacity. Well, if you go for a small battery capacity, of course, immediately your investment will be lower. You will reasonably get a higher DC current and also a short standalone time. Because of that high currents, also most likely your lifespan will be less than a larger system. If you have a larger battery system, your investment will also be higher. But the current, therefore, will be much lower. Therefore, also your lifespan will most likely be extended. So the trick is to find a balance between these two. what is too big and what is too high is basically a sort of a trial and error calculation. You have to see, well, what comes out best for you. If you look for a battery, basically what you do is you look for the needed energy over a total day, and then you're going to try out, well, what is the best battery capacity for my system? Well, you look at then what is the nominal discharge current and what can the battery handle, and don't overdo it, and what's the nominal charge current. Well, most of the time for lithium batteries, especially for the Victron lithium batteries, that's about half C. That means if you would have a battery like which on the picture, which is 200 amp hours, then the nominal charge current and the nominal discharge current would be maximally 100 amps. That means in 2 hours you will be able to recharge the battery, and when it was fully empty, and also in 2 hours you would be able to charge it again. Well, if you have a system and that system has to be converted to a hybrid generator system, this is a small example calculation. Let's say you have a 50 kVA generator, and it gives you a 50 kVA traditional generator setup needs to be turned into a hybrid generator system. Well, the average load on the traditional system in this case is about 10%, which is about 5 kilowatts. And if you look at them over the 24 hours, that would be 120 kilowatt hours a day. Basically, this is what you see a lot at generator systems, that they're running around about 10% of their capacity. Then you have to decide, okay, when is the generator running, if you have a specific time frame, and when specifically not. So when you have a quiet area, quiet time, then you have to also take that into the account. Running a generator is not always desirable, so how much time would you be able to encounter for that? Well, the running of the generator, not running of the generator, makes the battery most likely become larger. The more often you run your generator, the smaller your battery will have to be. And you have to make a few calculations to see, well, what's the optimal way of doing that? Well, in this case, let's say, because we have a 5 kilowatt hour of power on average, let's go for a 10-hour inverter usage. That means every 2 hours you charge, then 10 hours you go on the inverter side, and then you go 2 hour charge, and then 10 hours on inverters again. What you see then is that the battery needs to supply only the half of what you calculated in the beginning. So 120 kilowatt hours divided by 2. But of course, during the time that you're charging, the battery doesn't have to do anything. So basically, you have 10 hours of running that 5 kilowatt load, and then the battery needs to supply 50 kilowatt hour. The needed charge power for this, because you have to recharge the battery in 2 hours again, is about 25 kilowatts. So if you would have a 48 volt system, that would be 500 amps. The needed discharge power, well, that's an easy one in this case because it's only 5 kilowatts. That's only on 48 volts, it's only 10 amps. So that's for most likely, for most batteries, that's not an issue at all. Then what you have to see also, and what you have to check, is the load on the generator during that charging. Well, the load during the charging in this case is the 25 kilowatt you have to, well, refill into your battery for 2 hours, but also the 5 kilowatt that load is taking then, because the inverters are in pass-through mode, and that means that the generator is also supplying load to that load. If you do that, if you charge your battery with 25 kilowatts, you have to add more energy to that inverter, because in that inverter you also have a loss. That loss during charging is about, well, 15–20%. So in this case, that means that during the charging period, the generator will have to supply 35 kilowatts, or about 44 kVA, depending on your power factor. And that means that during the charging, that power is about 85% of the maximum of that generator. So you're running the generator already pretty optimal. So the charge current, like I said beginning, should be, well, about 50% of the battery. It depends a little bit on the type of the battery. Some batteries take more power and are happy with that, and others take less. In this case, because I chose for a 2 hour recharge, the charge current is about 50% of the capacity. That means 500 amps is needed to charge this battery capacity in 2 hours. Well, for example, if you would do that with 3 times a quattro 4815 kilowatt, which can charge for 200 amps, that will be fine. These are having enough power to recharge that battery in 2 hours. Well, the battery capacity you need is something else than the battery capacity that you have to install, because there is a depth of discharge. The depth of discharge creates that the battery what you install is larger than actually the power that you need. Well, in this case, let's say that the battery discharge should be about 90%. That means there's 10% of power left in the battery, and you would be using 50 kilowatt hours from that battery. That means that would be 1000 amp hours. That 1000 amp hours divided by 0.9, because of the maximum discharge of 90%, would mean that you have to install 1111 amp hour. So most likely in this case, that would be a 1200 amp hour battery to be able to supply the energy to this system well. If you have done that calculation, you can also say, okay, let's go for a smaller battery and see what happens then. Well, in this case, I decided to go for sometimes bigger battery and a smaller battery. First of all, the bigger battery. The bigger battery is based on 1 charge cycle a day, and 1 charge cycle a day means that you have to charge longer, but also that your battery capacity becomes twice as big, of course. So instead of having a 50 kilowatt hour battery, now you're using a 100 kilowatt hour battery, and the recharging, if you have the same 3 kilowatts, the 315K quattros, will take 4 hours to get them full. Well, on the application that I had before and this application, so the one in the middle, you can see that the amount of liters what you take to recharge the battery is equal. They both have to run for 4 hours. One has to do 2 hours and 2 hours. The other one has to run for 4 hours in a straight line. But it's about 9 liters an hour. That means it's 36 liters. So on the fuel consumption, that's exactly the same. But if you look at the battery becomes twice as big. Instead of having, 1111 amp hours, all of a sudden now you need 2222 amp hours. That means investment-wise, but also size-wise and also weight-wise, there's a huge difference between those two. You can also opt for the system that you say, okay, instead of having 2 charge cycles or 1 charge cycle, I'm going to go to 3 charge cycles. Well, if you would do that, you would be in total of 6 hours of charging per day, which means that if you're running for 6 hours, the generator will be used less on its load level. Instead of having then a 90% or an 80% load on the generator, because of the size of the battery, also the charge power will go down. So then you will be approximately around 50% of load of your generator. That means because you're running at a lower load, your fuel consumption per kilowatt hours that you're going to generate is worse. So now for the same amount of energy per day, you don't need 36 liters per day, but you use 43 liters. That means if your battery size gets smaller, which is nice investment-wise, and it's also nice weight-wise and volume-wise, it's a negative side on the part of the fuel consumption. So the balance lies, in this case, on 2 charge cycles a day, and then have a 10-hour inverter usage. For other applications, this can vary, of course. This is not always that 2 cycles is the best. It depends a little bit on what is the average load of your system. But what I would try to explain with this is that if your battery becomes too small, it's nice investment-wise, but it can have an effect on the fuel consumption. If your charge cycles become too less, that means that your battery becomes unnecessarily big and there is no fuel advantage anymore. A generator has a specific efficiency. The better you load it, also the more efficiency you have. The same, of course, is also for the inverter, but on a much different scale. If you have an inverter efficiency, you can see that also on the graph, especially at low loads, the efficiency is close to 100%. when you load the inverter more to its maximum, then it drops a little bit off, but it will still be around, well, what is it? 85, 90%, something in that range. That means saving power from the generator will not make up for the losses that you do in your inverter. So having an inverter in line with your generator will most definitely improve the overall efficiency of your system. These losses of your inverter are basically coming out as heat. So that's also a thing to consider. When you have an inverter with a specific output, in this case, let's say the 5 kilowatt again, that efficiency is about 90%. That means you lose 10% of that output energy, and that output energy, of course, should be powered to that inverter by the batteries, of course, and that means there is more battery power going in than AC power going out. Well, in this example, 555 watt on heat is being generated, and that is also heating up the space where these inverters are based in. So if you have 2 or 3 or 4 of these inverters in some system enclosure, that will be heating up certainly. Well, if that will heat up, it will also derate that inverter. So the more power is being used, the more warm you're going to generate, and the more heat is going to be generated, and also the less powerful your inverters are going to be. This is on the load side, how much power is being transferred to the AC, but also, and that's basically even more important, is during charging, because during charging, most of the inverter chargers running at full power, and that means the efficiency is worse and the power is higher. So also the amount of heat that you're creating then is also much higher. In this application, you can see that if it's running at 34 kilowatts, you have about, well, almost 7,000 watts of heat. Well, if you have 3 units, 4 units, 5 units, that will become, even more. A solution for that, of course, is to install cooling in the system. So if you have them in a container or whatever, you can install an air conditioning, and that air conditioning or a fan can make sure that that heat is dissipated, and also that the inverter is running at a higher nominal power. Often also the power of that inverter, sorry, the power of the air conditioning is making up for the duration of the inverters. So even though that air conditioning also needs power, the power that it needs is going to be added on top of the inverters because they run much more efficiently. What is extremely important if you have a hybrid generator system is that you have monitoring. Well, monitoring is one thing that Victron Energy is especially very good at. We have a device, something like what you see here, a Venus device, and this is a Servo GX. And a Servo GX is basically a computer, a small microcomputer, and that computer is gathering all the information from what is available in your system. So that's not only from your inverter, but also from your battery. That can also be the tank monitor. It can also look at power from your generator and so on. And with all that information, it can decide what the system should do. There's a built-in start-stop system in that servo as well. But the nice thing of this is that if it's connected to the internet, it will store all the data which is collecting in the system onto a web server. And on that web server, you can look at all the data over time. That means also you can do logging. You can also do settings changes, for instance, if you want to have the behavior of your system a little bit differently. But you can also connect third parties environment sensors like temperature sensors, tank sensors, and so on. So basically the monitoring makes you have more insight in your system. If you look at the VRM web portal, where all the data is ending, you can see what the system is doing. Because the important thing of monitoring is also that you can change the behavior of your system. You can say, well, I've chose for, well, a 2 times charging cycle per day, but I can also change that because I want to have the depth of discharge different, or I want to have the level when this generator should be started differently. You can all change that also from your web portal. More and more is being added to the web portal. Things like fleet management, things like operational information, all will be available from your web portal to be looked at. And that makes also, if you have more than one hybrid generator system, it makes it very efficient to use that. So if you have a system running with a servo in, make sure it's also connected to the internet so that you also have the proper data on your web portal. What is also possible for the web portal, and then it can make user reports. A user report is basically a sort of an overview of what the system has been doing over time, and then it can be used to prove the efficiency of that system. So it can tell you, well, how much energy did it use for a certain period of time, how much fuel did it use for a certain amount of time, and also compare that to if the hybrid system was not there, so as a traditional system by itself. What is also very useful is the use of widgets. Widgets are basically a small block of data, sort of a wizard what you can add on your smartphone. And with that smartphone, you can then look at the data on a very compact way, but a very useful way. You can also start and stop some applications with it. I have an overview here. And it depends basically on which widget you have installed. You can look at the generator itself. The generator has its own widget. You can start and stop from that. Also for ESS, if you would have an ESS installed, you can also look at what the ESS system is doing in graphs and also on values. If you have an EV station, you can also change the setting to manual or to automatically. Of course, you can look at your tanks, you can look at your temperatures, humidity, basically everything you have installed in your system. You can have a monitoring widget to have a look at that. And you can have a very fast overview on your smartphone with that. The next slide is a hybrid system report. This is an example of a hybrid system which is actually running. This one is running in the UK. And what you can see here that over time, is over a period of about, I think it was 39 days or something, the efficiency of this system is 77% savior on a traditional generator. That means real life data is being compared with, well, what would happen if that would be not installed as a hybrid generator system. And that is a great tool also to explain to people who are not used to working with hybrid generator systems, how these could actually work for your application. This is also a report which you can easily download from our VRM site. If you're installing a system, one thing you shouldn't forget is that you have to have a safety switch in. If something is wrong in your load or in your system which you're feeding, traditionally you can just stop the generator and then everything would stop. If you have a hybrid generator system and in an incident or something, you want to stop the load from being powered, you can stop the generator, but then of course the hybrid generator system will just take over and will supply that load anyway. So therefore you can use the safety switch. And the safety switch is basically a switch that you can connect to one of the units, and the units will then automatically stop all the other units. So this emergency switch is programmed into the master of the system. And as soon as you hit that button, all the inverters will stop. So even if the generator would still be running, then still the inverters will be disabled the power to the loads. So always make sure that you have a safety switch or something built in your hybrid generator system. Well, this is a small overview of your example of a hybrid generator system. What you can see here is basically that is not much different than a typical off-grid system. You can see the generator is feeding the inverters are feeding through a bus bar, a bus system in this case, the batteries, and of course you can also have the solar connected to that. In this application also the servo is connected to the internet by a GSM module, and also you have of course the display to operate the system. A lot of things, what you already see here, is something what most of our Victron energy installs already can do. So there's not much out of the ordinary in a hybrid generator system. The only thing which is important is that you have to find the right balance between your load and your battery charger inverter, and also with the cycles that you have on your inverter. But for a lot of people, having a hybrid generator system built or designed is nothing new. It's just the application might perhaps be new, but the system itself is not new. So, well, to end the webinar, basically, the question is, who can sell these systems? Well, basically, everybody with knowledge and experience with Victron Energy products can be, well, an expert in hybrid generator system, because there's nothing new to it. The majority of the products which are being used for hybrid generator systems are off-the-shelf products. The installation is about equal to marine or off-grid or industrial systems. Not much is different than that. The only thing is that the application itself is different, but the products and how you do it is basically the same. Also, the software for commissioning and monitoring is known to most of our installers and most of our dealers. It's, yeah, like I said, it's the same. We have the ability to use the VRM widgets, and of course, all these things are free of charge and unique selling points. There are not much brands who have the monitoring and the controlling of the system as well taken care of as Victron Energy has. So I would say take advantage of that and make the most of the systems what you already can make with these products. In short, you can deliver these systems. The market is there, and I'm convinced that the market will also will be growing over the coming years. More and more people looking at cost of fuel, cost of maintenance, and also the other benefits that a hybrid generator system will give. And I think we have a leading role with our product in this market. So yeah, please try and see also in your area if it's possible for you to integrate our products in these kind of systems. We have documentation. We have these brochures, what you see here on the right, and also we have the YouTube link. Later on, you will be also sent the presentation to look afterwards, but also you can use on that link to have a YouTube click on a small application example and how to do that. If you have any questions, if you have any things that you want to ask, please go ahead and ask our area managers. They all know of these systems, and they can help you also on designing and on helping if needed. So hopefully you will find this webinar a little bit contributing to the knowledge, and that you have something for the future. And in short, I would like to thank you for your time, also on behalf of my colleagues, by the way. And I hope that I see you soon, and that you have lots of success integrating these systems in the markets that you work. I will press the next slide. If there are any questions, I'm not sure how many questions there already were, but please go ahead and ask us, type us in the Q&A, and we try to answer as much questions as you might have. And again, thank you very much, and hope to see you some other time.